And let's go ahead and get ourselves started today. We actually have, I think, a fun session. This is stuff that I really enjoy working with. We want to start thinking about these buildings that we've been trying to create and really how structures actually work within those buildings, how we go ahead and support those buildings and really get the floors and the roofs and all the loads that are on them supported, and how we can sort of do that for buildings of a variety of different materials as well as shapes and forms. Because it tends to be, we'll find out as we're doing these things, fairly easy to set up some of these things. There's some very basic strategies we use for buildings that are relatively planar and flat and use very conventional geometries. And when we actually start thinking about some more unusual geometries, some more organic, biomimicking forms that some of the people are starting to think about, you need some special tricks and tools in your toolkit to be able to kind of do some of those things. Probably exploring some of those things too. So today what I'm going to start out with is to talk about some general framing system strategies for different types of materials, and out of that, then get into, within the modeling software, how we actually go through and set up those things. So you really see how to basically model either a wood frame building or a steel frame building or a concrete frame building, and then variations about how we do things to slope the roofs, or curve, or make trusses for all sorts of interesting forms. Kind of work with them so that you can have a lot of flexibility to support really whatever shape your building ultimately is. Okay, to get going with, we should talk about just really, in today's session I want to be talking about gravity load-bearing systems as opposed to lateral load systems. And the types of loads we're typically talking about here are things that are ultimately bearing on the roof or bearing on the floor. So it is things like, the live load that we are imposing by moving around in the space, and the load that's been put in here by the equipment and the furniture and the books and everything that's basically being pulled down by gravity. It also includes the dead load of the building. So just the weight of the concrete, the weight of the steel, the weight of the tile on the roof, all those sort of things. And it's really all about the loads that are sort of ultimately being pulled down by gravity that we have to support and kind of keep up. And as we do that, we're going to be looking at how we use columns and walls and beams and things like that to support the planes that have those loads on them. Okay. We'll distinguish that from lateral load systems, where lateral load systems tend to be concerned about things like wind or earthquakes, things that are actually sort of pushing sideways. And there's a very different set of, our approach to sort of handling things like that. In general, if you have a building, and it's kind of hanging around looking something like this. Here's on the ground. When we go through and we have all the gravity loads, it could be a combination of all the different gravity loads, but things that are worried about kind of coming on down, there's a couple of big considerations we have to work with. One thing is the whole notion of, is for those different loads, as we try to support those loads, is whatever we're putting those loads on really strong enough to go ahead and handle that? Okay? Because what's going to tend to happen is that'll start deflecting, it'll start sagging. And we have a couple of different big classic things we need to worry about. We need to worry about this whole notion of really just the shear that is induced by those loads. The shear is all about really what's happening out here at the ends where that's bearing. If we put enough load on there, we can actually just sort of break that right off. If there's not enough material right there at the corners, what can happen is, you can actually get a little fissure right in there that'll cause it to snap, and the whole thing will fail that way. It's really just, shear is all about the notion that if I have something and I put a lot of load here and I have a lot of load coming here, I could actually just shear that like a pair of scissors. Okay? And that's one thing we tend to worry about. The other thing we tend to worry about is something called just bending moment. How bending moment tends to affect things is, whether this is a beam or a floor plane, what will tend to happen is, as it sags more and more, as it bends on down there, what happens is, in the lower fibers, a lot of stress is actually pulling things apart from each other. So what will happen is you'll get little failures where it'll just break apart at the bottom. And as soon as it starts breaking apart at the bottom, it almost just rips through the material, because as material starts separating, there's less material resisting, so it gets worse and worse. So you have these failures where things just sort of snap. And if you've ever done that, when you... this thing? I won't do it with a piece of wood. No, I can do it. Got any wood in here? Nothing that I want to break. as you bend it down like that, eventually, yeah, it's going to go through and just break at the bottom there. It's interesting as you start thinking about these. Anyone who's been in the structures courses knows that there's different ways of resisting that. Like this is not very strong in that direction, but if I turn it up, it's actually very, very strong. And it's all related to the height versus the width, and there's lots of rules that will go into that. That's why beams tend to kind of have that shape as opposed to be laying that way. The final thing we tend to have to worry about, though, is deflection. And I think a lot of you are instructors know all this. What we tend to worry about is really just, for all this load, just how far down did that thing sag, and really what's considered acceptable for that to sag. And there's a lot of different rules for that. There's some rules that describe that as something like L over 360. So we take the length in inches, we divide it by 360, and we get the number of inches that it can sag, and that's considered acceptable. And a lot of building codes are sort of built that way. So that's kind of an okay guideline, so let's kind of think about that, what that actually means. If this thing were actually like 120 inches, now we call it 120 feet. It'll be easier in terms of what will be really long. Oh, no, 10 feet. We'll do 120 inches. Okay, we have some 10-foot beam. If we divided that by 360, what is that, like basically a third? Something like that. So that would basically say that this can sag like up to a third of an inch. Okay? And for most residential construction, that's considered acceptable. I'm not sure if you've ever walked through a building and kind of had the experience as you're walking along, you can sort of feel the floor bouncing along with you. A lot of buildings where they've kind of allowed very, low levels or high levels of deflection, it is a little bit springy. And that's kind of okay. It's not going to fail. It may make you a little bit uncomfortable. Okay, because people don't like to kind of walk on springy things. But yeah, that's just sort of a design criteria. A lot of people will instead insist that no, you need closer to like L over 480, okay, which would then give us a quarter of an inch. It's sort of tighter. You need more material to go through and do that. Okay. Especially if you're going to go through, where I run into this in sort of residential construction all the time is, if I'm going to put like a carpet floor or something like that, that's pretty forgiving. The floor can deflect a fair amount and it's not really going to damage anything. If I'm going to put a tile or a stone floor down, okay, if it flexes too much, then all the little grout cracks and the joints, they all start kind of rubbing and breaking apart and stuff like that. So we tend to use a higher deflection level there. But in any case, these are the kind of loads we're looking at. And to resist these kind of loads, we have these different strategies. What we can do is we can think about an entire plane and whether we can make that strong enough to resist everything. Or if we can't really make the entire plane strong enough, I guess this whole notion of adding beams or adding intermediate elements to help break that load up. So we can do things like put beams across supporting that. Or sort of extra strong. And if we need, we can even put beams in the other direction. Kind of strengthen it. And that's what it's really all about in terms of very basic framing strategies. We try and say, hey, we got these planes that are supporting loads. If they can't support the loads on their own, really, how can we add some support to them to go through and make sure that ultimately those planes aren't going to fail. So let's go ahead and I'm going to open up something that actually I put out there on the coursework website for you, if you want to grab it. There's a really good series of references that are all part of that basic building construction book that I love so much out there for you. And if you go out and take a look in session 8, you'll actually find sort of the section on floors, walls, and roofs there. And there's really some very good information there. So within this basic book, it talks about floor systems and the different types of systems, and we're going to be exploring those. And it's all about this notion of the bending and how we can really support those planes. But what you really tend to find is that based on the different types of constructions, there's different ways we can approach it. So for example, in what we're looking at right now in terms of concrete, it tends to happen in a couple of different ways. Concrete, it turns out, tends to be a fairly rigid sort of plane. It does a pretty good job about resisting bending and things like that, until you get too awfully far along. What tends to happen with concrete is we will often introduce beams that are going between the columns to go ahead and support things. Okay? And then within the space between, you have a slab that has to support loads. If there's no intermediate members, the loads could actually get pulled back to the beams on either side. That's called a two-way system. And you have to kind of design it as though it's kind of pulling in both those directions. Or we could go ahead and use a system like this where we have big beams on the sides and smaller little intermediate beams. okay, with a smaller distance in there, and then it's a one-way system. And it's a little bit easier to design the concrete that way. So the concrete has to have a lot of reinforcement to make it work this way. The concrete has to have a little bit less reinforcement in here. We'll put more into the beam. So it's kind of this trade-off between how much you want to put into the beam versus how much you want to put in the slab in terms of making that work. Okay. As we think about concrete systems like this, though, there's another variation. We should talk about that too. And that is something that actually happens with a type of construction we call flat slab construction. If you have a concrete slab, and you have a column like this, kind of coming up to it, and a column even above it. Okay. And you put a whole lot of load on it. Very often what happens is the slab can actually take the load. That's not the issue. The slab is actually not going to deflect too much and stuff like that. What will actually happen is you'll start having the shear being the bigger problem, because what happens is the resistance is all coming here. The load's coming down there. There's actually an incredible amount of stress right at that joint right there. So there have been a lot of problems with buildings collapsing because they're built with this kind of flat panel construction system. And what happens is basically little shear cracks develop that basically cause the entire slab just to kind of come down, and then this building sort of pancakes on down. So this is something in particular you have to watch out with concrete systems, is this whole notion of the amount of shear that we're introducing. You've probably seen in parking garages and other types of structures ways of dealing with this and not even sort of realize what they were doing. Like, can you think of any ways, if the problem is really that we're going to get some shear in here, okay, because we really have so much stress being transferred in a very small amount of area there, can you think about how you'd actually go through and like combat that, like right within the structure? There's a lot of good strategies for it, but can you think of any like alternatives? Yeah, the beams and stuff, they'll help in terms of distributing it around there. That actually works very well. Another way that kind of works really well is really just going through and just widening the tops of the columns. So sometimes you'll even see things like, this, okay, which we'll call a mushroom capital. And all that's really doing, it's not really, the amount of force coming through is still the same. It's just saying that really right at the point where we're trying to resist, as opposed to having to be carried over a very small area, and now we can actually be carried over a much larger area. So it's a lot less PSI. It's really much, much better. This is classically the problem. If you've ever had someone step on your toe with a high-heeled shoe, and how incredibly painful that can be, as opposed to the same person stepping on you with sneakers, no problem. And it's really this issue of just this very incredibly concentrated load and needing to spread it out. Now, that same principle actually is going to come back and haunt us a little bit later. When we come on down to the bottom of the building, and we have the ground down here, and our ground may be perfectly capable of carrying loads, but what it doesn't want to be carrying is like 10,000 pounds on that 1 square foot. So what we're going to end up doing at the base of our building is actually putting in some foundation systems that, again, are just all about spreading the load, because if we can spread the load, okay, then we actually have much less stress kind of on the earth. And we don't have a punching failure at the earth. So that's what really footings are all about. It's really all about just spreading the load out and making sure that we're not just punching through the earth. Because just so you have a good general guideline, earth is rated, it has its own, gotta think about it, whether it's PSI or PS, it must be TSF. Yeah, it has its own rating. You can study the earth, rate it, kind of really actually get quantitative data for what it is. But in general, if you can't rate it, you sort of assume it's like 2,000 PSF. In terms of what it can bear. And if you have more than that amount of load on a square foot, okay, then you need to go through and do something to spread it out a little bit. So just good little rules of thumb to kind of think about. So if, for example, we actually had, let's say there were 10,000 square feet or 10,000 pounds coming down from all the loads above, and we took it against 2,000 pounds per square F, what you have to do is basically size this plate, size the footing, just dividing that, so you need 5 square feet. It's kind of the general rule of thumb. It's like back of the envelope sort of calculations. We'll go ahead and show you how the analysis tools can actually be very precise about that, but just so you have some general guidelines about how to size it. So concrete systems, we'll probably look at them first. Some other systems, though, to look at that we'll also pay attention to are steel systems. And steel systems, in many ways, are very, very similar. Steel, we have these incredibly strong steel beams. We talked about steel being an incredibly strong substance. It really is fantastic in terms of its rigidity and what it's able to do. Very low deflection. It's very, very good there. We still need to go ahead and span across the steel. So we have things like, we have pre-classed planks we sometimes put on there, or a very common method you see in this picture is more, it's kind of like a steel deck, which is supporting a thin layer of concrete. Okay? And that system is just really designed to span between that small distance there. And it's, again, a very common way of doing it. You can do it with big old steel beams. If you don't want to have big old steel beams, you can do things like these. These are like little bar joists, which are open web joists. But again, same sort of basic principle. We try to basically figure out a way to subdivide and carry the loads back to stronger elements and ultimately come on down through the columns. Even our friends doing wood frame construction do the same sort of thing. We tend to have all these things that we call joists, all the wooden joists. They'll come across and bear on a beam, and that beam will ultimately come on down to a column typically. Wood, in fact, all of these sort of have this attribute I should point out though. Sometimes we go ahead and bring them across to columns. Okay. Other times, we can bring it back to a wall. Okay. And especially in residential construction, we tend to use this technique an awful lot. We actually bring the joists back to and just have them bear on a wall. Let's talk about why that is. Okay. If the amount of load that is coming through the joist and actually at the end of the joist bearing down is small enough, you actually can bear on the wall. It really is sort of a question of loading. Because what happens is, it's really this. I'm going to draw a picture of a wall for you. Walls, if you strip away all the sheetrock and stuff like that, actually look like this. They tend to have, two wooden members, two-bides we'll call them, at the top. They have all these things called studs coming down, typically at every 16 inches. Okay. And then on top of that, you'll have all these feather members, these joists that are coming across and bearing on top of it. So super. We'll go ahead and put those on top. Here's my joist. Here's my joist. Here's my joist. Okay, we often draw them like this to kind of show they're on end. Okay. And everything's pretty cool in this scenario because in this scenario what's happening is the load that's coming down here is coming right on top of there. Things are super. Everything looks fine? Okay. Until, of course, what ends up happening in the field is no one pays attention to something like that and they put the joists out here. Okay, still at 16 inches, just offset a little. Now, how big a difference can that make? 8 inches. You know, it can't change anything very significantly, can it? But what ends up happening is we have the support right here, and we have the weight coming down right here. And now we start having a problem. And what problem does this look like? It's kind of like that problem over there. It's a shear problem, where basically things start breaking, and it's not really that big a difference. It's just that if you don't have enough material there, it can shear and kind of break away right there. So it's actually sort of interesting. If you look at really most of the catastrophic building failures that happen, they're probably more shear related than anything else. Not because people didn't try hard in terms of their basic planning, but sometimes when things get offset just even a little bit in the construction process, shear gets introduced where it wasn't planned to be. And that results in this failure that no one anticipates. You know, there was a very famous case back in the 1980s of it was a Hyatt Regency Hotel in Kansas City, and I know that because that's where I'm from, where there was a skywalk. Okay, so here's what they were doing there. They had this lobby of a hotel, they had some big beams at the top, the floors down here, and they actually had this notion of there was going to be a sky bridge, some sort of floor, and there was going to be a bridge over here. Okay, looks pretty good. We need a way to support this. So they said, we've got an idea. We'll go ahead and have these threaded rods. It'll come on down. all the way, and we'll hang it over here, and it'll come on down. It's going to be perfect. You know, and actually steel's very, very good in tension. You can put a lot of weight on steel. It'll kind of respond very, very well there. And it was sort of a beautiful design. It was going to be engineered. You know, it was going to work very, very well. However, somewhere along the way, someone said, you know, making a single 20-foot rod out of, you know, threaded steel and kind of weaving it up there, that's not going to be very easy to construct. So I got an idea. Won't make any difference at all. What we'll do is we'll go ahead and make these a little longer, and we'll just go ahead and, you know, just offset it just a little. What difference could that make? It's an inch. Who's going to notice? And the problem is no one did notice. It made it all the way through the shop drawings, and no one really caught the fact that they had offset it by just a little. So what ended up happening on some big party night, you know, when everyone's up there swaying and dancing and having a grand old time, they actually introduced enough force here that it caused a little shear failure there. And this lower one fell. And again, you know, the point isn't to be horrific in terms of telling the story. It's more just to sort of watch out for it. What always gets you in this stuff is it's not your fantastic design. It's really what happens somewhere on the line when someone interprets your fantastic design and doesn't realize how important that design intent was. Yeah, so you have to be careful about that stuff. But that's gravity loads. Let's go ahead and think about how we would model a building relative to gravity loads. And to do that, how about this? I have a model of a building out there. It's out there on the server, and I would love to have you open it up because we are going to frame it up in a number of different ways and ultimately figure out like some variations on a theme. So this building actually is somewhat similar to some of the buildings I was looking at the other day with people. Yeah, don't worry about the architecture too much right now. We'll just go ahead and take a look at it from the standpoint of how we're going to be dealing with the structure. The idea is we have some walls on the front and we have some walls on the back. I want to have a big old curtain wall on one side of it. That might be the south side. It would probably be useful to have some good shading features over here because that much glass is kind of looking a little troublesome. Okay. And inside of that structure, we have a couple of different things we need to support. For right now, I'll just go ahead and let me go ahead and just take the roof off of this right now for you. In fact, I could do that in a number of ways. Let me kind of show you different ways you can do that. Sometimes I hide these things. I tend not to like to hide things very much because I get in trouble with them later. I could say just hide that view. What I actually tend to do, just so you know, if you want to kind of do it too, is I turn on something called the section box, okay, which is like that little shoe box which lets me scalp the building. And then I can sort of push on down and sort of see inside that way. Either way, just whatever you like. We're just basically trying to get a view of the building inside so you sort of see just really where that is. Okay, so here's what we're going to do to this building. We actually have a couple of different things we need to sort of take a look at. We need to take a look at sort of this lower floor, this middle floor, and ultimately supporting the roof up there because those are the three different surfaces that are going to have some sort of gravity loads to them. For right now, I'm going to leave the floor, the lower floor, mostly alone. I'm going to say that, hey, it's going to be some sort of concrete slab. Okay? And again, that may or may not be true ultimately, but we'll start with that, and we'll go ahead and figure out what we need to do about that in just a little bit. But let's go ahead and take a look at these other floors and kind of think about how we are going to handle them. Okay. Let's even think about this in terms of a concrete building first. That might be the easiest to think about. As you look at a building like this, and let me even kind of scale it in the other way so you sort of get a sense of really how this little balcony overhang looks. Kind of push it in this way. That's interesting. I'm not sure why I see that, those other, oh, it's the section box. That's why it is. Let me hide the section box just so I'm not looking at that for right now. Okay. As you look at something like that, and we think about trying to support that second floor, let us kind of think about what's going on. We do have some things to work with. We have some walls to work with, and again, depending on how the loads are, we might be able to work with those walls, and partly depending on the materiality of the wall. if it was a light frame wall made of like foam and stucco and things like that, that wouldn't have the weight, so the bearing capacity to support the wall. If it was a concrete wall or a block wall, it probably could support that wall. But as you look at this kind of big floor plate that's kind of in the second floor, you know, any ideas about how we can go through and support that? As you look at it, you know, what does it suggest to you? It's not so bad this way, it's kind of long that way. Like, you know, any number of ways you can do it. Give me an idea. How do you think we ought to go through and support a floor plate like that?
Put some columns under it.
Okay. Put some columns under it, you know, maybe on the front side here. Got it. And then how often would you guess we should space them? Could be. You know, there's an answer to it. That's pretty good intuition about what it's going to be. Something like that. You know, the closer we put them, the less stress is going to be on the slab. The further we put them, the more stress is going to be on the slab. There's a trade-off in there. You can kind of go either way. But let's start with that. We'll just go and put some columns in there and we'll figure it out. So if we use that kind of approach, let me even go over to level 1 and we'll start thinking about this. Okay, a very useful thing as I'm looking at the floor plan to get started with is, if we're going to start putting the columns and kind of put the building together, it's actually 100 by 50. It's pretty, just so you know, this is about 5,000 square feet. It's kind of the size of our building. You know, it's almost about 8,000 square feet so far, but we can add some more to it. Okay, a very good thing to get started with is, before we start putting the columns down, to actually think about an overall grid system, an approach to really how to sort of subdivide this building. So as you do that, we often divide things into a grid, and the gridding tool is up over here. It's on the architecture tab. And usually what I do when I'm doing something like this is I just start putting grids in, and we can adjust them in a little bit, but I draw them from the tail to the head. So I'm going to put a grid over here. I'm not going to put a grid right on the outside. It's sort of a choice here. It really depends. If you think the outer wall is going to be bearing the load, you can put the grid there. If you think that you're going to have columns on the inside, you tend to put them where the columns are going to be and have the outer wall kind of hanging out from the column grid. Okay, but the grid tends to be based on sort of the notion where the columns are going to be. So I'll put one there. Maybe I'll put another one over here. Another one over here. I'm just going to draw some in there. Again, there's no kind of hard and fast rule about this. Okay, it's 100 feet. Maybe 4 is enough. Maybe I need a 5th one. I don't know. What do you think? 4 or 5? We'll take votes. Everyone for 4? Anyone for 5? Okay, 5 it is. Now, I'm putting these guys in here. Oops, I go back to level 1. You might be saying, okay, I'm laying them down here. They don't look like they're very evenly spaced. You might want to evenly space them. Let's go ahead and do that. So what I will do is, if I can sort of get the 2 end points about where I want them, I could go through and try to manually figure this out and kind of do the math to make it all happen. Another way to do it that actually I recommend is you can just go ahead and use a dimension where if you go dragging between them, like that, you can actually say just make it evenly spaced. So, just a quickie way. You can do that manually and kind of figure it out, or you can use dimensions to kind of drive those and make them evenly spaced. Either way. Yeah, when they are evenly spaced, I have a hard time actually telling what the dimension is. We go ahead and kind of turn that off. Once it's spaced, it'll keep it every 23 feet. Okay. At least it turned out to be a whole number. People are always happy when it's whole, even feet, as opposed to, no one likes 11/16. It's one of those things where, or 15/16, people know you made a mistake somewhere. Nothing is ever 15/16. It's the way it is. Okay, let's go ahead and put some grids in the other direction. You might ask, well, where should I put the grids in the other direction? Kind of hard maybe to tell in floor plan view. If I go to the second floor, I might have a better sense of where I want to put the grids in the other directions, because I sort of know I want grids in the back and I know I want them in the front, but where I want them to be relative to that balcony is kind of hard to tell here. So I'm going to go to the second floor level and put the grids in there. So again, we'll just come on over and do the tail to the head. I'll put them sort of towards the back over here. Now, as I'm placing them over here, you notice it sort of just made that grid 6. I tend not to like that. I tend to like those to be alphabetic, so I have like a nice grid that kind of says A1, A2, you know, just kind of works in an easy way. 1, 6 is harder to figure out. So I'll make that A. And what will happen is as I put the additional grids in there, it'll make them B and C. So again, we'll go through, put those grids in. I'll put this one just sort of towards the front of the balcony. I'm not going to put it right on the edge of the balcony because I'm actually thinking I'd like to have these columns be a little bit back from the balcony edge, just not right at the front edge of the balcony. They don't have to be right at the edge. Cantilevering is a wonderful thing. Go ahead and take advantage of it. So it's probably architecturally a little more interesting if they're back just a hair. They could be towards the front. Actually, we should even think about this just as our overall strategy. Let me put the other one in and I'll go back to section and we'll think about it. You can think about this because you do have a choice about, I'm going to put this last one in. That'll be C. In 3D, I get sort of a choice in here. In my mind, maybe not in your mind, I was thinking about these columns just going from like first to second floor. But maybe at the upper level, just having longer beams that were going to span the entire thing and not have a column going up. But you know, it's kind of a choice. You can go either way. So I can either support the balcony with some intermediate columns and keep it open, or I could have those columns go all the way up. Again, what's the trade-off? If I have them go all the way up, the beams at the roof will be a little bit smaller, but I have these columns in the middle of my space. If I don't put them all the way up, then I have this expansive, very open space that might be more interesting architecturally, or you can put a heavy-duty structure up at the roof to kind of take care of it. And that's okay. Okay, so for me, I'm probably going to go up to there. Okay, so how are we doing in terms of some basic grids? You got some basic grids? Yes?
Could you show me one more time how you space them all evenly?
Sure. What you do is you go through and we take a dimension. So under the Annotate tab, just grab a string. So grab 1, 2, 3, 4, 5. Get the whole bunch of them. Okay, and when you place that, it gives you this option of really making them all equal. And if you turn that on, then they'll all be equally spaced. No worries. Okay, so we are ready, if we have some grid locations here, to place some of these columns in here. And if we're going for concrete, let's go ahead and find some nice concrete columns we can work with. We're going to do the same building in steel in just a minute. So let's try the concrete ones. Oh, I'll go to the Structure tab, and we'll find that the columns are really just a type of element. And within there, you'll see by default it's kind of choosing some sort of wide flange steel shape. But there's no reason we have to kind of stick with that. We can come over here and, well, doesn't look like there's much else loaded in here, so let's kind of load in something else. Like we do with most things, if we don't have what we need, we can go get to a family. And you'll actually find inside this structure folder, structural columns. Let's find some concrete ones, and we have some nice interesting ones here. Let's take a look at them. We have a rectangular column. We have a rectangular column with a drop cap. That's this whole notion of like kind of putting a cap at the top to sort of spread the load around. We have a round column, a square column. That's got a rectangular column. It's got a drop cap, and it also has, I call that like a little mushroom at the top of it. It's got that little spreading to get to the drop cap. Okay, but I'm just going to go for the round one right now because I'll go for round columns and actually put the beams in as opposed to just trying to kind of doing it all with the slab itself. So, choosing the round column, say OK. We got some sizes here. We can stick with 12 or 18 or whatever we think. How about 18? We'll go for that for right now. Again, later on our structural analysis software can give us the right size, but that might be good for what we intend architecturally. And we are ready to put some columns down. So as I think about those columns, let's go dropping them in here. Okay, there's this notion as we place them, it's that whole thing about, do you think like an architect, do you think like an engineer? Where architects tend to go to level 1 and put things up from level 1, engineers tend to go to level 2 and put things down from level 2. But it doesn't matter, the same thing happens either way. It's just really whichever way you want to think about it. I'm on level 1 now, so I'm going to put them up from level 1. I'm going to choose height. Let's think about our heights. we can go through and put them all. The ones that I want to have go up to level 2 are these 5 towards the front of the balcony, because I'm not going to have them run all the way up. I'm just going to go to the balcony floor. So I'll choose level 2 and just go ahead and put them in there. You'll see that if I actually sort of hover over the intersection, it seems to grab the intersection. It knows and tries to snap to the intersection of column grids. Columns like column grids. That's just they like them. They try to gravitate towards them. So you can place them in there. Let's come back over here. I'll put one at that intersection. I'll put one at this intersection. And I'll put them at all the intersections. Or actually, the intermediate intersections. Now, for the front and the back, though, I'm actually thinking of having to run all the way to the roof, though, so that it's going to be, up and up the whole level there. I could do it in 2 separate chunks. I'm going to do them all the way up. Okay, so we're sort of pouring them all at once. I'll think about whether I like that in just a second. So I'll say that it's going to go up to level 3 and start putting them on the back. Now, another way to do this that actually saves you some time if you want to do it is you can just say that you want to put multiple of them on there and put them at intersections. That's kind of a quickie way because it just sort of grabs the intersection for you very quickly. You can say that you'd like to place multiple of them at grids, at which point you can just go ahead and choose that grid and maybe I'm going to intersect it with this and you'll see that it's going to choose them all. It just puts them at all the intersection points. So that's a quick way to get the back ones in there. I'll just say finish that. I'll go over to 3D and just kind of see how we're doing so far. Okay, so it looks like I have some big old columns towards the back. I have some shorter columns here towards the front. This back, again, is sort of, we could have gone either way with this back wall in that if we wanted the back wall to be load-bearing, we probably could have gone through and omitted those and actually just sort of put a strong structural wall back there. Yeah, depends on really what you want. If you make it a strong structural wall, you have a little less flexibility in terms of the glazing and how you work with the screen. If you carry it through the columns, you have more flexibility in the screen. If you carry it through the wall, you have less flexibility. So it's going to sort of decide really what you want in terms of your design freedom. The front side here now, there's not a whole lot of question on the front side we got to do something because on the front side here where this big old curtain wall is hanging out, that thing is not good for carrying loads on down. So we do have to go ahead and put some sort of columns there to support it. And even here, actually we saw an interesting choice here. I should have asked it really. I should have presumed the columns were good on the inside. We could have put them on the outside just as easily. Maybe that's a nice architectural feature. Maybe I'll change my mind partway through and decide to do that instead. And how I would do that is, as opposed to putting that column line in here, I can just go ahead and grab that column line. I'll just pull it out onto the veranda. And then I'll place the columns out there instead. So again, I'll say, what are we going to do? We're going to get these columns. And again, I could either sort of place it at the intersection. I'm going to say multiple and just do, I'm going to choose this grid. Then I'm going to control click to get that one. Oh, it's interesting. Will it not do it because they're not actually intersecting? That's funny to me. Conceptually, they intersect. Even if they don't, I have to stretch it to make it intersect. Vertical columns at the grid lines. And now again, okay, now they're all there. And I'll finish that. So let's take a look at that in 3D too. Where are they? Oh, they're probably sitting outside my section box right now. Like in terms of where they are. Let me go ahead and unhide the section box so I can, wrong one. That's the grid. Yeah, there it is. Here's my section box. Okay, so now I have the columns kind of hanging on the outside. Now, we've made this look pretty easy so far. You're saying, well, this is great if all my columns are straight. What if my columns aren't nearly as straight as this? What if they actually start slanting or they start doing interesting other things? Can I put in columns that do things like that too? And the truth is you can. let me go ahead and show you how that looks. Oh, let me even just turn off the section box so you can sort of see. For example, I have all these columns kind of hanging around out front here. And if, for example, I wanted to put in some diagonal columns, I wanted to do something that was a little bit different, architecturally, I could do something like that. If I want to put in a column that's diagonal, what I can do is say column, and say slanted column instead of vertical column. Still has all the same type things, but what I like to do is actually do this 3D snapping, because that makes it really easy to grab things. So I can say I want the bottom of that up to the top of that, and start making some sort of like a groovy super truss across the front of the building. Okay, so they don't have to be vertical. They can be slanting if you want to, and that's okay. But again, not saying you have to do that. Just want to give you an option. In terms of understanding, you can make some things slanting. Okay, if we are going through and we got all our columns in place, the next thing you typically have to do is go through and put in some beams. Again, do we need the beams? It really sort of depends on the question of the load and the slab, and can the slab transfer things to the columns without punching, or do we need the beams to help support the loads of the slab and carry them? And if we want to go through and add in those beams, yes?
In real life, we would never, pour a two-story concrete column, or would you? Like, you wouldn't, like, go
Actually,
to your building
it depends. Yeah, it's less common to. Exactly. That's why I was sort of torn in my own mind there as we're going through and doing that. Yeah, they probably would do it one floor at a time. Although, no, for the front here, they actually would. Yeah, it's really more back in there where you have the slab. So I will take your comment and say, maybe it's better to actually take those columns on the back and just bring them level 1 to level 2, and then copy them up to level 3. I think that's actually probably better as a reflection of the true construction. Yeah?
At least on my model, and I think I might have seen it on yours, the ones that only go up to the first story look like they go through the floor.
They kind of poke at it, don't they? Let's talk about that. Actually, let me fix a couple things here. One is, for these over here, we take your comment seriously. We'll go through and grab these. And to be a better model, because I want to think about the poor person who's going to have to actually use this as a construction model later on. Okay, I'm going to take all those, I'm going to bring them down to level 2. Okay, you see they're still going to be doing that little bit of poking. Let me copy this, and I'm going to paste them up to level 2. Is that going to work? Nope. Damn, I always get that wrong. It's that thing where I think of them as being from level 1 to level, it thinks of them as being on level 3, is really what's going on. So let's maybe paste them onto level 3 instead. It's again, it all has to do with how you think about it. Oh, come on, you. I don't want to do that. Where did modify go? Paste to level 3. Okay, so let me get that one. Okay. That took care of our constructability comment. Thank you. Okay, as far as those poking things go, let's talk about that. Yeah, they do kind of appear to poke out, because what happens right now is the very top of that column is completely fused and is exactly at that same level. So we could do a couple different things. We could go ahead and say that we want to go ahead and lower that to the bottom. But even better than that, the more common way to do it is actually, with concrete especially, we join them together. Okay, because really the way it's going to work, and it tends to work, is that the columns will be poured, the beams will be poured, the slab will be poured onto it, and it sort of fuses into like some monolithic assembly of all those different things together. So if you want to do something like that, what you need to do is a couple different things. I'll take my floor, let me change it to be concrete too, because I think that's part of what's going on there. I'll make it cast in place concrete. Just if I'm going to be good about this, because if I just fuse them and join them out of 2 different materials, it'll do it. But again, it sort of creates something that's a little bit odd. Okay. You still see them though. So what I want to do is basically just do a join. And how I do a join is I say join. I can join that to this. At which point it's really just considered one big object. Zoom out a little bit. So again, I could do a join here. That. So a number of other ways we could do it. The other way you could do it is you could say that you want to attach the column to the bottom, at which point it will stop it. It really depends whether you want to think about it as being a single object or keep it as two different objects. So that other strategy would be to take it and just say, oh, I got to find where the attachment goes. Attach the top or the base and kind of attach it to that, at which point it just sort of, it cuts it at the bottom or at the bottom of the slide. Either way. Okay. So good points.